Hello, students. Today we want to discuss some of the properties of polar coordinates. As I said in lecture, we began with parametric representations of functions, and we channeled that into how we could rewrite some of the arc length formulas and area formulas from our previous work with functions. And as I said before, these types of topics will have a huge impact on your work later, especially in physics and calculus 3 and other engineering type classes that you may take, or just purely mathematical classes in differential geometry and topology. So again, just remember that as we work through these ideas, you will see these over and over again, just like calculus, integrals, derivatives, limits, things like that. You will see them over and over again, and every time you see them, you'll get that much better at it. So let me go ahead and share my screen so I can basically review what I've already talked about in class. The main thing with polar coordinates that we find to be a little bit different is just the fact that when we talk about polar coordinates, we have a distance r, which will be directed, and that will make us think more like vectors. So for those of you that have plenty of background in physics, I think this won't be a problem. And even if you don't, it will certainly pay off as you do take more physics. Now, the first thing I want to note is that with polar coordinates, we continue to think like the XY plane, but not exactly. For instance, the x-axis or the positive x-axis will now denote the polar axis, and the origin that we usually think of as 0, 0 will be the pole. So we will talk about tangents at the pole. And then as we think about the unit circle and our standard representation for measurement along the unit circle, or the congruent idea, which is that of an angle measure, we'll think of measurement that will move, like I said, via S1, where we'll have an angle that's 0 radians, and then we'll move like we're headed to the positive y-axis, which will be angle theta equal pi over 2, and then we move to the negative so-called x-axis, where we have theta equal pi, and then of course we keep moving in a counterclockwise direction, and then we have theta equal 3 pi over 2. The idea is that we can think of the positive, negative, x and y axes as kind of being in the background, just to orient us like we're using the unit circle. So I just want to make you aware of that, so that as you work problems, you can make that correlation. So like I said before, R is actually going to be directed. It can have positive and negative values. And the second coordinate with the polar coordinates will be the theta, which I just spent a few seconds talking about, which will be the theta that we remember from the unit circle. So when we think about the coordinate pair in Cartesian, we think x, y. When we think of the coordinate pair for polar coordinates, we think r, theta, r comma theta. Now, what's interesting about the polar coordinates is the directed distance aspect. So we can think truly of r theta as being a point in the plane. And now, before I actually start talking about that, I want to give you an idea of how we actually entertain the idea of the additive inverse. In some cases, like when I give you some examples, r will be positive or it will be negative, but just take r to be a real number and theta to be a real number. What we want to do is think of physics when we think of the negative or additive inverse of a vector, it simply reorients the vector in the opposite direction. That is, you basically have a rotation of pi radians. And so you think of a vector here going in this direction and its additive inverse, the blue pin here going in the opposite direction and being of the same magnitude. So we can think of that correlation between a vector and its negative, just like we think of the directed distance in polar coordinates, and this is how we'll do it. So if we have a theta and we have an additive inverse, just like I described, we will think of the addition to theta as some odd multiple of pi radians. And what's usually convenient is just to add or subtract pi, because those are easy multiples to keep up with. But again, any odd multiple that you add of pi that you add to theta will definitely be correct. So I think it many ways to describe this, but I think it's easier if you think of the additive inverse of r comma theta will be equivalent to the ordered pair r and then theta with the addition of the odd multiple of pi. Okay, this is very important because, again, this is how we utilize the negative of a vector by basically reflecting it. If we think of the head of the vector and taking that as like an origin, we reflect it through that origin and move it here. So again, it's going to take a little bit of getting used to, but that's what we think about when we have directed distances. So you can look at these real simple examples here, just using this definition. We would say -3 comma pi over 3 would simply be 3. That is, you remove the additive inverse, and then you can simply add a multiple, an odd multiple of pi, which here I just added pi. And then, of course, pi plus pi over 3 is 4 pi over 3. Okay, so again, we usually just take the k equal to 0 and we add the odd multiple by having just 1. Or, you know, of course, we could take k equal to -1 and get negative pi, and that would be even just as convenient. Now, another thing that you remember about the unit circle is that we do arithmetic modulo 2 pi, because as we think about the distance around the unit circle, we have a distance of 2 pi radians. It's so amazing when we do mathematics and we have pure numbers, and how we try to go between degrees and pure measure, where degree is just a way of taking the unit circle and dividing it into 360 pieces. And we still have a pure measure, but we have to come up with some way to distinguish them. So we use a little uppercase O for degree, and then of course when we do radians, we don't use anything, or sometimes we just write radians. So we develop complexity because certain numbers in our mathematics are pure in that they are part of the underlying theory. Nothing that we've had to create, they're just there. So we get to use that with polar coordinates. So that would be telling you right off the bat that polar coordinate representations, just like angle representations, are not unique, because you can always add a multiple of 2 pi to theta and you have an equivalent angle. So you're thinking, oh man, that's going to make it more complicated. Well, not necessarily. It just means that there's flexibility. And we're grateful for that flexibility, but because of the periodicity of the unit circle, we have trig functions which are periodic, and those are unique objects. Periodic functions are, well, we'll just say this, they are convenient because they have certain properties that make them easy to understand. We don't think of the trig functions and the hyperbolic functions and the inverse trig functions and the inverse hyperbolic as being completely simple, because they can get very complicated. but there's a certain uniformity because of the periodicity. Obviously, the hyperbolic functions aren't periodic, but they mimic the standard trig function. So that is a help in and of itself. Now, with the idea that we think of the Cartesian coordinate system as just being an overlay on the polar coordinate system, we have the very simple trigonometric ideas that we have from the unit circle, which you already know from your study of trigonometry. So when we think about a radial distance, that's just Pythagorean. R squared equals x squared plus y squared. And then, of course, the angle is the same that we have in standard trigonometry. The theta will just be the inverse tangent of y over x. So this is all repetition. But it's a convenient repetition because we can look at the polar coordinate transformation, so to speak, as a unique way of transforming integrals when we get to calculus 3. There are all kinds of hidden magical properties that we can use as we do mathematics, and this is certainly one of them. Now, of course, if we just look at the trigonometry here, we can define cosine theta as x over r and sine theta as y over r, just like you did again in trig. And so that would just mean if you cross multiply, or, you know, when we're doing our physics, we tend to focus on these equations since it's really easy to manipulate this in your head. So we have x as r cosine theta and y is r sine theta. So we can move between these two representations as we have an invertible transformation. So again, when we think about starting with Cartesian coordinates, we can move from the Cartesian to the polar using this. If we start with the polar coordinates and we need to move to Cartesian, we can use this. So again, this was already built into your trigonometry from long ago. So that's one thing, or one aspect about polar coordinates that are very simple. Now, before we move on, I just drew up a sheet to give you an idea about what I was talking about. I think that makes this a little bit simpler. When we think of the polar plane, so to speak, again, we think of the pole here, and we think of the polar axis, where theta is just equal to 0, just like we're thinking about the unit circle, or you can think positive x-axis. And then, of course, we can think of theta equal pi over 2 as corresponding to the y-axis. So again, what you're seeing is that just in and of itself, polar coordinates can be very useful because their description of certain objects, geometric objects, are very simple, like lines can now just be replaced with a value of theta, and we're done. And then, of course, r would be free, so you get the expanse of the line. And then, of course, you could think of theta being free and r equal 1. Well, if r is equal to 1, that's the unit circle. You just get the radial distance, and theta has any value you like. And so r equal 1 gives you a very simple polar equation of the unit circle. So therein gives you simple examples of how polar coordinates can be very, very useful. And again, like I said before, you'll use these more and more as you continue in your mathematics. Now, what I've done here, students, is just without loss of generality, I'm just assuming that r and theta are positive, and I just take what we think of as a first quadrant representation. Even though we're not really in the standard Cartesian plane, it certainly helps us to get our grounding. So we can think of r theta being here, where again we have a distance r, which I can note here, a distance r, and then a measurement of theta. And of course, theta is measured just like you normally measure it from the positive axis here, the polar axis, or thinking about trigonometry, the positive x-axis, and the counterclockwise motion being positive, and in the clockwise being negative. So all of that is exactly the same. You would think it would have to be this way. We can't change the rules for a new coordinate system because we want to be able to take all the mathematics we've already developed and use that. So of course the consistency is required. Now, you'll see lots of things when we talk about polar equations. Usually that's just going to be R equals some function of theta, or we could say F of theta equals R, where we would want to think of how we could possibly sketch a picture of a polar curve. And you're going to find that to be actually very simple once I share some information with you. So you might be thinking, would there be symmetries and all? Well, we can think of the symmetries that we have in the Cartesian plane. So for instance, if you were thinking of the fact that there could be a symmetry in the polar axis, that is if you replace R theta with R negative theta and got no change in the actual curve. Well, again, if you want, you could think, well, let's just replace R with its additive inverse, and then we could add a integer multiple, odd integer multiple of pi. I was just going to say add pi, but I'm trying to remind you that we get kind of lazy if we add or subtract pi because it's so convenient. But this would be the easiest odd integer multiple of pi to use. And so we would see that replacement by either of these coordinates would be a good way to check for symmetry in the polar axis. Again, using the definition here. Again, let me just say this. When you put in the additive inverse, then you apply the definition to add the odd multiple, integer multiple of pi. And of course, I'm just, in this case, I was just kind of lazy and just said, I'll just add negative pi. And so of course, the pi and the negative pi absorb and we get this. So the idea is that you can write things that are equivalent using the definition of directed distance, which we have here. So there's nothing difficult about it as long as you think of vectors, and that will always make things easy. Now, of course, if we think of a situation of having symmetry in the theta equal pi over 2 line, then we would think of replacing R theta with possibly negative R negative theta. Well, what is that? Why does that work, or why would we think that would work? Well, now we use the definition of the additive inverse of R, so that'll be R, and so I'll just add a multiple here of pi, and we get pi minus theta. So basically here, we're thinking of again, rotating into this side of the polar plane, which is thinking like second quadrant, and our trigonometric ideas tell us that this is just the ordered pair R theta, pi minus theta, which is equivalent to this. So if you were going to think about checking symmetry in the line theta equal pi over 2, you could use these coordinate transformations. So just subtle changes, but very much like you did before in Cartesian. Now, another thing that we might think of having maybe symmetry in the pole, or like origin symmetry when we think of Cartesian coordinates. So we might think of replacing R theta with negative R theta. But then, of course, by applying the definition to remove the additive inverse, we just add a multiple of pi to theta. And so we get R comma theta plus pi. I always say the theta first, even though I've written the pi first, forgive me. But again, you can see that that's just moving in a counterclockwise direction to here. So when we think of R just as being positive, then it's easy to think of what we did in trigonometry. But the negative, again, is always reflection, always gives us the reflection in the pole. And then we can take the definition of the additive inverse of R and transform that into, again, R with no additive inverse with the adjusted angle. And so again, if we wanted to check symmetry in the pole, we could check these coordinate pairs and check to see if there was no change in the actual equation or polar equation. So hopefully this is helping you to see how we deal with the polar plane, very much like the Cartesian plane, with the added property of r being directed. Normally, our distances have always been positive. We think of geometry or zero, non-negative. The directed distance is something new, but it is certainly a property that makes the polar equations very useful and arithmetically very pleasing to us. So good. So now, what we want to do is think about just some very simple examples. I just basically want to make sure that you can do the very simple coordinate transformations. So for instance, as you work through your homework, even though these are somewhat dry and boring, they're very important just to be able to work well with the new coordinate system. So for instance, you might have a problem where you're given a polar coordinate pair. Here we've got -4 and we have -3 pi divided by 4, and this is our r theta. Now again, when we think about this, we're like, okay, well, let's go ahead and write this problem in a way that will be convenient to us. Now, if we think about this particular problem, notice what I've got here up in the box, convert to rectangular. So maybe to make the problem a little bit simpler is to first use this. Let's just write definition here because that's what we're using. We're thinking of this as we would vectors. So again, we can remove the additive inverse and add pi to -3 pi over 4. And notice now, when we add here, we get 4 comma pi over 4. So we're thinking first quadrant. We can always run back to the Cartesian plane and get orientation. Where does that actual ordered pair, polar pair actually exist based upon Cartesian? So you can always think about an overlay of that just to help orient what you're doing. So now, again, we have an equivalent representation here, polar representation of what was given to us. And so now we can go to the Cartesian by using the transformations which we just talked about. So we know x is r cosine theta and y is r sine theta. Now, these are very simple. And of course, if you don't have, for instance, values that are convenient to you from the unit circle, you can write the expressions exactly. And don't worry about decimal approximations or anything. So when we have the convenience of simple values that we're aware of, then we'll use that. So now, of course, we have cosine of pi over 4, which is 1 over √2. And so, of course, √2 will absorb into one of the two factors of 4 to give us 2 √2. And then the same for y. Again, sine of pi over 4 is 1 over √2, and we get y is just 2 √2. And then, of course, we have a first quadrant Cartesian pair, 2 √2, 2 √2. So again, nothing difficult here, something that you probably already thought about before, but now we're doing it based upon the definition of a polar coordinate system. Now, we just did another one here just to get some practice with this. We have convert to rectangular. And again, it's good just to practice to make sure that you know how to do the transformations utilizing the definition of directed distance. Remember, you can move things around with angles and always be able to provide the correct range of theta. So you have lots of flexibility working with additive inverses of r to adjust the value of theta. So always feel free to do that. It's not a complication, it's actually an assist. So here we do the same thing again. We have -2 and we have 11 pi over 6. So let's go ahead and remove the additive inverse. And I just got a little bit lazy here. I just said, I'll just go ahead and subtract the multiple of pi. It's odd multiple, good for us. And so, of course, this is just 6 pi over 6, and 6 from 11 gives us 5. So we have 5 pi over 6 here. So now again, we're thinking this, we're thinking, okay, well, we're using the unit circle. We've moved in the so-called second quadrant. Again, thinking about trigonometry. And so now we have x is r cosine theta, y is r sine theta. So now we just do the computation cosine 5 pi over 6, which is negative root 3 over 2. And then, of course, sine of 5 pi over 6 is 1/2. So we get values for x and y, which are negative 3 and 1 respectively. Or excuse me, the negative square root of 3 and 1 respectively. Again, a Cartesian pair that's in the second quadrant. And so we have what we call the Cartesian equivalent. Like I said before, the polar representation is not unique. When we think about a point in the Cartesian plane, we get uniqueness. So even though we have different ways of writing the polar representation, we're only going to get one of these when it comes to Cartesian. So again, that may be very obvious to you, but just think about that as you're doing these problems. Now, what we have is just, again, I've got not unique here, but not a surprise, right? So we have convert to polar. We've got 6, -2, which is a Cartesian point. And then, of course, what we see, the x is positive and the y coordinate is less than 0. So that puts us in the fourth quadrant. Okay, so that's what we're thinking about when we want to have a representation for a polar coordinate pair so that we get an equivalent representation. So first, we're thinking if we've got the Cartesian, we substitute the Cartesian to give us the so-called polar, using our equations that we talked about before. So r squared is just x squared plus y squared. So we have 6 squared plus -2 squared. That gives us a 40, or 4 times 10. So now, of course, r can be whatever you like, plus or minus. So we've got r is plus or minus 2 root 10. And then, of course, we look for the inverse tangent of y over x. So we have a -2 over 6. So that gives us an inverse tangent of -1/3. Of course, now we know in this case that the inverse tangent is an odd function, if you like, but be that as it may. Notice here, when we think about theta, we know that the inverse tangent runs between -pi/2 and pi/2. So this is actually in the fourth quadrant. This is a fourth quadrant angle when we think about trigonometry. Again, we think of the range of the inverse tangent function. And again, we're thinking this here. So that's really convenient to us. Now notice what I've written here. I've got a negative here, but of course it's also an odd function. So if you wanted to, I'll just go ahead and write this down. That's a property you prove in trigonometry. The inverse tangent function is odd. So if you like, you can do this too. So now if we want a fourth quadrant representation, we can take r to be 2 root 10, and then of course the negative inverse tangent of 1/3. Now, of course, we're thinking, how can we get something equivalent to this where we get lazy? So we'll take the additive inverse of 10 root 2 and have -2 root 10. And then, of course, we want to be able to have an equivalent set up here. So what we can do is just add a multiple of pi. And lazy as it sounds, it actually works very well. So now, of course, and remember, I've done the inverse tangent exactly. I don't have a decimal approximation here. So we're trying to do this so that we get an exact answer. So if you like, you can write down as many representations as you want. Any odd multiple of pi would work here and give us an equivalent expression for this. So I just use pi here. So again, just think of the additive inverse as being the reflection in the pole, so to speak, like a vector. So this gives you a nice way to use the arithmetic of the polar coordinates. So it's simple, but very useful. Now, I just wanted to make a comment here. I started to write these things and then I changed my mind as to what I want to say. Thank goodness for our convenience of whiteout. Now, one thing that we have is with parametric representations, which is now basically what we have. When you think of it, X equal R cosine theta, Y equal R sine theta. Well, it's parametric in the sense if we want to kind of step back and say that now we're thinking of R as a function of theta, okay? So if we have that, then we can apply the theorem for the Cartesian derivative that we learned about in the previous section. So again, we can apply the chain rule. So again, we're thinking of the polar equation here, and then taking the derivative with respect to theta, okay? So again, we're thinking of R as a function of theta, and of course, theta is theta. So now, remember, when we do the Cartesian, we have the y prime divided by x prime, and then of course now, some of our problems, we used a variable of t. Here we have a variable of theta, so that should not be a surprise to you. So by the chain rule, this is very simple, but very important, or at least something that's unique to what we've already been working on from our previous section. So we can apply the chain rule here to get x prime, which would just be r prime times cosine. And then, of course, leave the r alone by the product rule and take the derivative of cosine and get negative sine. So this gives us r prime cosine theta minus r sine theta. Now, if we look at this, we can do the same for sine. We'll just get y prime is r prime sine theta. And then, of course, the derivative of sine is cosine, and then we just get r cosine theta. So now remember, we take the Cartesian derivative, or we can actually write the standard Cartesian derivative utilizing, let me check the focus here, make sure that's nice and, there we go. We can now take the ratio of x prime to y prime, and we have this just using these two equations. Now, what we're interested in, and this is important for tangents at the pole, r is equal to 0. Okay, and this is what makes this so simple. It's like we're just making this up, but we're thinking of how could we, or can we define tangents at the pole just like we have tangent lines for Cartesian graphs? So r would be 0. We can determine tangents at the pole. But now what's important about this is that if r is equal to 0, these two terms are absorbed. But then that means that the r prime must be non-zero. Otherwise, we'll end up with a cusp of pathology, which we've already seen in our previous examples of the epicycloid and the cycloid. So that's kind of a thorn in our side, but not a bad one. It certainly makes the graphs a little bit easier to draw. So now what we can see with this stipulation here, so we don't get the indeterminacy, the r primes, as I've noted here, absorb as we see from here, and that just leaves us with sine alpha divided by cosine alpha, and then we have tangent alpha. Of course, assuming that alpha is a zero of the polar equation. So now, of course, we think of the Cartesian equation y equal tangent alpha times x, a line through the origin if we're thinking Cartesian. But of course, if we solve for alpha, that's just the inverse tangent of y over x, which again, we write as an equation. So we just say theta is equal to alpha. So getting tangents at the pole require, again, we have to be a little bit specific. We have to make sure that the r prime and the r equals 0 at least give us something that other than zeros. For instance, we can't have all of the alphas that make R zero making R prime zero. We don't have the bona fide tangent at the pole. I mean, we can think of having, infinite tangents and things, but when we have cusp and things like that, then we don't have a bona fide tangent. So again, just like we did before when we were looking for points of horizontal and vertical tangency or values of the parameter where those would exist, we certainly had to throw out the ones where the values were the same because that gave us the indeterminacy or the pathology, which again would not give us what we're looking for. So again, that's where, as you see down here in this example, cusps. So we'll talk about that shortly. So again, when you're looking for tangents at the pole, we're just looking for zeros of the polar equation for which R prime is non-zero. So that is what it is. Now, I'll have an example of this later, but this cardioid is an example where you have the situation of the pathology going on where you get a cusp here because you don't get the R prime of theta or alpha being non-zero. So let's look at some examples of these types of graphs that we're interested in. I gave you a sheet during lecture which summarized the graphs, and I want to talk about some examples. In lecture, we've already talked about a circle on the polar axis or the so-called positive x-axis where we have R equal A cosine theta. And we also showed by doing a replacement using the transformations that it was a Cartesian equation of a circle. So these are quite simple and very useful. Now, of course, if we want a circle on the theta equal pi over 2, that again is tangent at the pole, then we can just take R equal to A sine theta. And if you did the transformation exchange, then you'd also complete the square and get a Cartesian representation of the circle. So we've already talked about these, but these can be very convenient, especially when you're doing calculus problems, because they're easy to spot. And we can also say, as I noted in lecture, the Cartesian equation is fine, but when we look at this and see how simple it is, we're like, I'll take this. And then, of course, x squared plus y squared equals 1 is the unit circle, but we can replace that with R equal 1 or negative R equal 1. I mean, it's like, I'll take the simpler one. And in many instances, our descriptions can be so greatly simplified by using polar coordinates. Now, the other types of curves that come up quite often and are more simple in the polar representation are the limacons. You saw the cardioid, the little heart shape, but you can have limacons with an inner loop, kind of a dimple, and then just kind of a morph circle. And then you can have the rose curves, which are very simple. The idea here is that you have multiple angles, just like you studied multiple angles in trigonometry. So you have R equals A cosine n theta or R equals A sine n theta. So what we've noticed here, which is very convenient, when n is odd, you get n petals. When you have n even, the trigonometric equation gives you 2n petals. So again, interesting that we have that. I think again, this chart just simplifies the process of allowing you to refresh yourself with the simple equations and go right to what you know it's going to be and poise your work to support that. Now, one thing that we have here with the circles are the lemniscates, and I'll say something about that. We can still get graphs of these without having to suffer from just plotting points. We know that mathematics is replete with patterns, and we use those patterns to lessen the amount of work or make the work more efficient. So let's do some examples of these, and I think you'll find what we're going to do is just use the concepts that we have from trigonometry, and you're going to find these to be very, very simple. Now, the first two, we're going to have a cardioid or a limacon and a rose curve. Now, as I said before, when you actually do these, the sheet gives you some relationships between the A's and the B's here as to whether or not you'll get an inner loop or a heart shape or a morph circle or whatever. You don't have to memorize that, but it does help you when you're looking to get a quick graph, basically knowing what the result's going to be. Now, what I can suggest here is a very simple procedure. That is, most students will think, well, can I use the Cartesian graph to get a simple polar graph? And the answer is yes. So for instance, if we have something simple like this, we have R equals 4 plus 4 cosine theta. What we can do, since R is a function of theta, we can think of the Cartesian graph, and this is where you use your trigonometry. You do a sketch of the Cartesian graph, which will now give you very simple values of R, and then use the arithmetic of R to plot some very simple points on the polar curve. And it allows you to trace R as the values of R change and the values of theta change. And students will often say, well, how far do I need to draw my graph? How, do I need to full period, half a period, what? Well, what I usually say is maybe draw a period, and then what you're going to find is that these polar graphs will start to repeat. Again, they're periodic. And so you just draw until you've completed the curve, so to speak. You know what it's going to be, and once you start retracing, then you're done. So don't think you have to draw a certain amount, just draw enough. And if you need to add to it, then we'll do that. Now, a very simple graph here. Notice, if you like, this is the standard period. We just have a theta, so we know the period is 2 pi. And what you can do is simply look at this and say, well, let's just get some simple points. What you do, you think of the principal points, 0, pi over 2, pi, 3 pi over 2, and 2 pi. That's just basically taking the period and dividing it by 4 and getting the simple points along the unit circle, because again, we don't want to do too much work. So again, when theta is equal to 0, we get the 4 times 1 plus 4, which gives us 8. So we have a value of R here, which is 8. And you're thinking, when you draw this, you just develop a very simple scale and increase and decrease in a manner that allows you to get a reasonable sketch. This is not going to look like a computer depiction, of course. So you want a reasonable sketch. And if your heart shape is too rounded, well, again, you're not looking for perfection. As long as the sketch is arithmetically correct in the sense of what you're doing as far as where you have intersections of for instance here, theta equal pi over 2 and the polar axis, then you'll be in good shape. Now, as we look at pi over 2, of course, cosine of pi over 2 is 0, so we just get 4 plus 0, which is 4. And then, of course, at pi, we have negative 4 plus 4, so we have a value of R, which is 0. And then we have 3 pi over 2. Again, cosine of 3 pi over 2 is 0, so we just get 4. And then back to 2 pi, we have 4 plus 4. So now what we can do is we can draw this based upon these simple values. Now notice here we have a theta of 0 and a radius of 8. So we can look at this as just being, a value of 8. Here's 4, here's 8 at angle theta. And now what's going to happen as we move to pi over 2, we're seeing that the radius is decreasing in value. So we can move with a shorter and shorter radius and move to pi over 2, where at this point we're at 4. Now, here's where you have to think of this. As the theta is getting larger, the value of pi is getting smaller and smaller. And so you can think here is we've got r equal to 8 when we have theta equal to 0. So you can say r equal 8, theta equals 0. And then as you move along, you can have a value here of, say, like maybe pi over 4. You can do like, just kind of just guesstimate here. So we have, in this case, r will be a value between 4 and 8 here. Notice we can just write it out explicitly. So if we say theta equals pi over 4, not that we have to do this, but I'm trying to show you that this rather casual sketching will be more than sufficient to get a beautiful curve. So at pi over 4, we have r is equal to 4 plus 4 times 1 over root 2. Again, that's what we did before. And of course, that's 2 root 2. So we have 4 plus 2 root 2. So that's our value of r here. So we can just write r equals 4 plus 2 root 2. And then as we continue to progress around to theta equal pi over 2, notice we have a value of 4. So at this point, we have r equals 4, theta equals pi over 2. Now, you don't have to be this particular as you move through. Notice as you draw this, you're going to think, well, this is going to have polar axis symmetry, and that's fine. And you don't even have to verify all of this, but these particular curves are simple and they possess great amounts of symmetry. So you can check that too, as I've noted here. Remember from the very beginning, going back to the symmetry, if you wanted to check that, you can replace r theta with r additive inverse of theta, which is simple. That's usually the easiest way to do, but you could see cosine is just a even function, so that negative would absorb. So you would know that there would be polar axis symmetry. And this is always nice to have. Just to reference, just to think about, so that you can always look at a curve and say, well, I expected that. Now, of course, as we continue, you notice here, as you move to pi, the value of r is getting smaller and smaller until it decreases to 0. And notice here, all the values here of r are non-negative. So we don't even have to, as we say, project through the pole, because the definition of additive inverse is not required here. So this is really nice. And then, of course, using the symmetry, knowing that we have polar axis symmetry, the curve is just going to repeat. Whatever we have up here will be duplicated here, because we have polar axis symmetry. And even if your curve is not beautiful, it will certainly give you a representation that is solid. So again, when you look at your examples for your special polar graphs, we're looking at something like this. And then, of course, as the values or the functions change, sine and cosine, it can be oriented differently. And as the pluses and minuses turn around, it can be oriented differently, because that will necessarily change the graph here. But you don't have to worry about this. This graph gives you values of r and the associated values of theta. That doesn't mean, or doesn't require for you to do a long drawn out table and then plot points. The plotting of the points is a waste of time. We use what we already know about trigonometry to get a quick graph. And then, of course, now as we move back to 2 pi, as we move through here, again, notice we have a value of 4 at 3 pi over 2, where this is the value of theta, 3 pi over 2. And then as we move back to 2 pi, we ascend back to the value of 8. And so we have what we call the heart curve, and we have the cusp here at pi. So when you look at zeros here, again, of the polar curve, those zeros correspond at pi to a zero of r prime. And that's why we get the cusp here. Because we notice when we do tangents at the pole, if r of alpha and r prime of alpha are both zero, then we have the pathology, we have the cusp, we have the indeterminacy, which gives us this picture, which again is very pleasing. Again, the heart shape. Now, for the rose curve, and I thought I would just do a simple example here, and this is a nice example where we can get tangents at the pole, because the curve is nice enough that we get that, and you can just, all I did was just draw them in. It's very simple. But again, notice when it comes to doing tangents at the pole, we simply look, as I've noticed here, for zeros of r, and when you draw your Cartesian graph, you can notice here I've written tangents at the pole at the zeros of the polar curve. Now, you notice here we've got the polar curve 0, but we don't have r prime being non-zero. That's why we don't have one of these. So again, it's very simple to find tangents at the pole, and usually that's all you're asked to do. But you still need to verify if you're not sure, or if you think you've got a curve that has the heart shape or the cusp, then you're good with that. Now, notice here, and this is what I was talking about before, where we have the multiple angle. Again, 3, the coefficient of theta is odd, so this would imply that we would expect 3 petals. And so now, when you think about this, and you think about the new period of this, we know the standard period of cosine is 2 pi. And so when we divide by 3, we get 2 pi over 3. So notice here, 2 pi divided by 3 here. And you notice I've written it up here. And so when you divide by 4, to break it up into those nice intervals, so you can just use the simple values on the unit circle, we definitely get some simple values. So notice here, if you will, we've got 3 times 4, but that's just 6 times 2. The 2's absorbed, and we get pi over 6. So these intervals are just length pi over 6. So you get in this case, notice here, 1, 2, 3, 4, 5. So or in the sense of the points, 1, 2, 3, 4, 5, and this gives you a complete curve here. So notice here, this implies, let me just write this out so you can see why I wrote this. The first point is 0. The second point is pi over 6, and I don't reduce this. And then 2 pi over 6. This is how I teach trig, but not everybody takes me for trig, so I'm just trying to review this, and then add another 4 pi over 6. Now notice here, I've reduced these, thinking about these as you would on the unit circle. But if you write the points here of the broken down period, so to speak, or the partition period, then it's easy to plot additional points if you need them. So now what I've done here, you see that I've got one period, and then I went ahead and I started drawing a little bit more. Notice here I've got r equals 0, r prime not equal to 0, which gives us the tangent at the pole. So that's really important. That's a nice hypothesis. Tangent at the pole. So it's really important to have that hypothesis, as we see with the Cartesian derivative. Now, what we can also notice is that this will allow us to draw the actual polar curve. Now let's look at this. We start out, and again, as you notice what I've drawn here, I can add additional points if I don't complete the curve, is if I don't start to retrace things, or I'm not back to the beginning, so to speak, then I can add more to the curve. So notice here, I've added some additional points here, but I didn't go all the way up to 8 pi over 6 to have 2 complete periods. Let's see if this is enough. And so now at 0, we start out at 4. And of course, you can do any scale you want. In my pictures, it's not going to receive any accolades from the art world, but it is sufficient. So we start out here at 4 when theta is 0. And notice as we move to pi over 6, which I've noted here by the tangent at the pole, the value of r just simply decreases. So we move back to the pole here. Okay, now notice, this is where we're thinking, okay, at pi over 6, as we go to 2 pi over 6 or pi over 3, we get into negative values. So here's what's interesting about this. We move here, and then as we think about moving to pi over 3, which is here, we've got to do the projection in the pole. So we're not coming out this way because r is negative. We have the additive inverse. So now we start moving in this direction. So again, we've got a very, very smooth curve at the pole, no chinks, no problems where we're kind of hiccuping. As we move from here, we smoothly move down to another value here of 4, but opposed to pi over 3. So this is 4 pi over 3. This is adding the multiple of pi. So this is why our definition is consistent. It makes sense with our trigonometry. So just remember, because now we can read the values of r as being less than 0, we move this way. And notice as we move back to 3 pi over 6, which is pi over 2, that takes us right back to 0, where we have the angle pi over 2. So again, smoothly moving here, then here. So I can let me just kind of get that first bit here. So here, and then all the way back to here. Just like that. Nice and smooth. Using this piece here, all the way to here. Now, of course, after this, we've got this little stint from what, 3 pi over 6 or pi over 2 to 5 pi over 6, where we've got positive values. So we don't have to do any projection in the pole. So now we can start moving again. Again here, notice 4 pi over 6 is 2 pi over 3. So we move from here all the way to here. So this sketch is simplified by just using this curve. And then we decrease, 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 decrease back to angle measure 5 pi over 6, where again, r is 0. And now you're thinking at this point, look how much we've drawn. Start keeping with the red, we've moved here. And then all the way back to here. And the only piece that's left is just this last part of the petal here. And so we look at 5 pi over 6, and we're thinking, okay, as we move to pi, we're going to have to project through the origin. So now notice at pi, we would actually be here if we had a positive value of r, but we've got a -4 value, so we have to actually end up here. So as we move for the last bit here, angle is moving this way as we move down, thinking of the unit circle, but the projection is through the pole, just like thinking of a vector. And so now, instead of moving out this way, we complete the curve or the petal, and then we end up opposite theta equal pi over here at basically theta equals 0. So again, utilizing the values of r, we can very simply think about the projection through the pole to complete the curve. Now, using this to get this is simple. Trying to plot points with no organization in mind is not suggested at all. there can be many, many ways and strategies to draw polar curves, but what we want to do is utilize the fact that the curves are so beautiful and they have so much nice symmetry. Notice here, you can just see by what we've drawn that this has the polar axis symmetry. Okay, again, with the cosine, we get the polar axis symmetry. Cosine's an even function, so that's like 3. Okay, so again, by utilizing the Cartesian graph, we can get a very, very nice picture. And then, of course, you can go back and redraw it and make it look beautiful. But now you can go ahead and add in the tangents of the pole, pi over 6, 3 pi over 6, or pi over 2 here, and then at 5 pi over 6 here. So you can add the tangents at the pole just by using the Cartesian graph. Again, the Cartesian graph, as we think of just overlaying that on the polar graph, gives us orientation as we draw the curve. So just remember, though this curve looks very complicated, and if we were to think of trying to draw this with a Cartesian equation, it would not be useful to us. I mean, when we see an ellipse in Cartesian equations, hyperbola or whatever, that's fine. But we've already seen now with parametric representations in curve theory, we have better ways to describe them. But now you're seeing as a polar curve, this is the way to go. So we are opting for the polar coordinates because polar curves can be very, very simple. It's like, well, now we call them polar curves because we use polar coordinates, but everything doesn't start out this way. Coordinate systems are developed to make their implementation and use simpler. So we see a very beautiful connection between the polar curve and the corresponding Cartesian curve, where we think of R as being dependent and theta as being independent. So you're using what you learned in trigonometry to now give you a boost to do a polar curve and simple based upon what you already know. Now, the very last curve that we want to talk about, again, I've got some more information here. You think I'm interested in symmetry. Remember back here, I did the same thing. I keep referring to this because this will be very useful to you. But I again write the same thing down here. When we have the symmetry, we get the no change. And so that was just my way of showing you that however you want to come about it, it might be best to think of it this way. But that again is your choice. Now, this last curve is called the figure 8. And students tend to have a little bit more trouble with this, but let me make it simple for you and give you a way to think about this so it's not very difficult. Now, one thing again that we see here, we've got corners with the Cartesian. That is, we don't get the beautiful tangents at the pole here because we have kinks at the pole. And notice here, when we look at, for instance, the Cartesian curve, and we think about, where we have zeros, the problem is that as the curve evolves through the pole, the transition is not like the rose curve. It's not a smooth transition. It's like a hiccup, and then it kind of clicks going in a direction that's not smooth. So this is an example where we don't have the beautiful tangents at the pole, and you can do more work with that. And I've talked about how you can do some further analysis here if you want to do that. But I want to show you how we can get this curve very simply using just basic trigonometry and algebra. The curves are written implicitly, just like when we think of conic sections, we always write them implicitly as the standard quadratic equation. And then we look at particular branches, or particular portions of the graph that are actual functions. So so the key here is like, okay, this is written in the implicit form. How can we use trigonometry to do it? So here's one way of thinking about this, and this is certainly not the only way. If you think of doing the square root property, notice here I'm just looking at the positive square root, so to speak, 2 square root sine 2 theta. And then I cheat a little bit because I know if I take the square root of the sine 2 theta function, the zeros are going to be the same. The curve's not going to look exactly the same, but what's positive will stay positive, and the negative parts won't make any sense. And if we're looking for a real curve, we would need to move to the complex plane to see that. And so we're utilizing real input, real output. So what I suggest here is a much simpler way to do this. Again, we have the 2 theta, so now we see that we have a period of pi as opposed to 2 pi. And what I've done here is when we divide the pi by 4, we get these simple points, just like we had with the rose curve. And so what I do, we've got 0, pi over 4, 2 pi over 4, 3 pi over 4, and 4 pi over 4, which we just basically plot here. And then, of course, we're thinking, oh, I see, you're going to use this to get the values of R, and we'll be good. Now, another thing that you notice here, this is a figure 8 curve, and you're thinking you've got the symmetry through the pole, and I keep going back through here. If you replace, of course, the R with its additive inverse, then the curve doesn't change, which is clearly the case. So this is not a surprise that our curve will look like this. But let's just see how we can easily get that using the construction that we have for the previous examples. So now notice, as you draw this curve, okay, if we think of one period, and I've got 2 periods here, we see from 0 to 2 pi over 4, and then from 4 pi over 4 to 6 pi over 4, we have non-negative portions. And then, of course, in between these non-negative portions, we have negative portions. And that's where we have to say, okay, that part of the Cartesian graph will not be represented in the real plane. So this is how we can get a fairly simple graph just utilizing what we already have based upon the Cartesian graph. So now notice, as I've written here, oh, the light goes off because I'm not moving around. Notice here, I'll just say in the negative portion, no graph. We don't get any contribution here. But to make this simple, again, the square root of 4 is 2, so I have my little cheat graph to help me out here. So notice we start out at 0, and then R grows to a value of 2, and then diminishes as we get to 2 pi over 4, which is pi over 2. So notice, very simply, we start here because we've got the sign at 0, and then we grow, and I'll just go ahead and do this in another color. We grow here up to a value of 2, so you can think of this as R equal 2, theta equal pi over 4, and then we diminish the value. Again, remember R is related to the value of theta, and so it will, as theta changes, the value of R will just move out, increasing, decreasing, so you get this beautiful petal, and we end up with the figure 8. But how beautiful it is and how simple it is when we look at it this way. But now notice here, at this point, we've got square roots of negative numbers which aren't represented. Now, this is where you can see the key that occurs at the pole. That is, we don't have these beautiful tangents at the pole. They don't exist. So here at 4 pi over 4, or pi, we notice, again, we're at 0. But then as we extend to 5 pi over 4 to come out here, the value's getting larger, okay? And so we're thinking, are we moving this way? No. Here, as we move to here, instead of coming in a very, smooth way, we're kinking up and going this way. So the value here at pi is moving out this way. So as we get larger than pi and we move to 5 pi over 4, we're doing this way. So that's where the kink is. So instead of being a smooth transition here, I'll just say this is the kink. It's like you have a hiccup. So you have a very non-smooth transition there. And that's why we don't have the occurrence of the tangent, the polar tangent. And so now as you continue to move, again, as we get here to 3 pi over 2, we move all the way back up here and we're done with the figure 8. So I can look at this and say how simple this is if we simply look at the square root of the original function and then apply trigonometric properties to get a square root graph. Again, we know that our square root graph won't look exactly the way I've drawn it, but it simply gives us the values of R that make sense when we try to plot this. And so now we have our figure 8 curve, which has the kink at the origin, but that's okay. We still have a nice simple curve, and this curve is very, very simple. Again, you think about replacing everything with x's and y's, you get x squared plus y squared on the right-hand side. And then, of course, the sine 2 theta, you can use the trigonometry to write that as 2 sine theta, cosine theta, and then replace everything. And you have an equation that is mired in x's and y's that is hard to describe. So again, when we think about these beautiful curves, we think about how elegant they are in the polar coordinate transformation setup. That is in polar coordinates. I don't have to say transformations. We see how simple they are using polar coordinates. So again, we think about the simple circles here, and then just R equal 1, which is just the unit circle that's centered at the pole, so to speak. We think about the lemniscates. Again, if we have the cosine, then we get the figure 8 that is saddled on the polar axis. We get our Rose curves. We did a Rose curve with the sine function, so it did not exist along the polar axis. Again, these curves are very, very simple in polar coordinates. And then, of course, the limicons, the dimples and the inner loops and the quasi-circles, so to speak. Again, what I like here, special polar graphs that have a simple polar form. And so as we talked about this in lecture, we just finished our infinite series, and now we're doing parametric equations and polar coordinates. Very, very different. But what's beautiful about this is that as you move on in your mathematics and engineering, you've got new coordinate systems. You've got to deal with coordinate systems that help you solve problems. And then, of course, all of the other calculus that we've studied will find its way into your differential equations and partial differential equations. So as you continue to work through this, the only thing we have left is that now we want to apply the calculus of arc length and then the area when we actually rotate a curve about an axis to find its area. We want to now see how are those impacted when we use polar coordinates. And what we'll see in calculus 3 is that all of this will be generalized and we won't have to work as hard, but we're going to use some very simple trigonometric relationships and also our theorem about the Cartesian derivative to transform the arc length and the area into the polar coordinate forms. Again, it seems a little bit much, but right now we don't have the utilization of the change of variables for double and triple integrals. So we have to kind of hang back. But you remember when I talked about center of mass, I cheated a little bit. I said, you know, ladies and gentlemen, this is really what's going on. And I may say something about that in lecture that we have on Monday. But just remember that everything we learn has its place as you continue. You may not use it every day, but it will certainly have its place. And I hope you've enjoyed the polar coordinates. We'll say more about this in lecture. I think this is kind of fun and a very nice application of what you learned in your previous courses. And we are done. Thank you.